And now I can get rid of that. And so here's what we're going to talk about. Well, the new concept we're going to talk about is average atomic mass. So average atomic mass is the number that we see on the periodic table. It's on the bottom. It's usually not a whole number, but sometimes it is. Average atomic mass. And
this is the average atomic mass. It's the number on the bottom of the periodic table.
What this is kind of the number of contributions that each isotope makes. And so the way we're going to calculate this is we're actually going to take the mass of, let's say, yellow times the decimal contribution of yellow. Then we also have to take into account the other contributions. So I'm just going to add this down here. So we're going to have the mass of orange times the decimal contribution of orange. And then, as you can imagine, we're going to do the same thing with green. So we're going to take the mass of green, and instead of the names, I can use the symbols. So mass of green times the decimal contribution of green. And then I would keep going on. So then I have green down, so I'm going to take blue now. Mass of blue times the decimal contribution of blue. And then we have one more isotope that's stable. So here's our mass of purple times the decimal contribution of purple. And that will equal our average atomic mass. Generally, our average atomic mass is measured in AMUs. I'm going to call this R just for now, just as a placeholder, because R is kind of like the rainbow. And what I can do is I can sub in all these numbers. So instead of calling it average atomic mass, I'm going to say AAM is equal to the mass, which is, remember, the mass is made up of the nucleons. So for yellow isotope, it's going to be a mass of 1 because it has 1 proton. And I'm going to put that in parentheses times its contribution in decimal form, which is 0.1. And then I'm going to add to that the contribution from, that was the contribution from yellow. And then the next, I'm going to add the contribution from orange. So this would be 1 plus 1 is 2. That's roughly its mass is 2 because it has 1 proton, 1 neutron. And then I'm going to multiply its contribution in decimal form. So 0.2. And then I'm going to continue to do this. So I'm going to do green next. Its contribution is going to be 1 proton plus 2 neutrons. So it has a mass of roughly 3. And then I'm going to multiply its contribution, or its decimal form percent abundance. So this is going to be 0.3. So we can see this one is kind of doing a lot of heavy lifting. It contributes a lot. Then we go on with the blue one. And I'm going to actually shift the blue one down here just so I have enough space. But for the blue one, it's going to be 1 proton plus 3 neutrons. So it has a mass of roughly 4. And then I'm going to multiply that by its decimal form contribution. So 0.2. And then I'm going to also add the purple. And its contribution, or its mass times its decimal form percentage, is going to be 1 plus 4 for the mass, which is going to be 5 times 0.2. And that will give me, again, my average atomic mass in AMUs. So, when I do all that, I can see that for yellow, its contribution is 0.1, because 1 times 0.1 is just 0.1. Then I can add in the orange. So the contribution for orange is 2 times 0.2, which is 0.4. That's its total contribution. And then I'm going to add in green's contribution. So green's contribution is 3 times 0.3, which is 0.9. You can see it contributes a lot because it has the highest percentage, right? There was the most of this isotope. And then we're going to continue on, and we're going to add in the blue. The blue had a smaller contribution, but it has higher mass. So we'll see that skews things a little bit. So this is 4 times 0.2. So this is going to be 0.8. Again, not the biggest number, but you can see, even though it has a smaller contribution, it skews it a little bit more. And then you will see our purple. So our purple has the same kind of thing going on. It has a mass of 5. And then we multiply that by its decimal form percent abundance. And we're going to get 5 times 0.2 gives us 1. And so that's what we get here. And when we add these all up, the 0.1 plus the 0.4 plus the 0.9 plus the 0.8 plus the 1, that is going to give us a mass of 3.2 AMUs, right? So if we just do some quick math in our head, these two make 1. This one plus this one make 1 point. So this is 1.0, this is 1.2, and then this is just 1. So 1 plus 1.2 plus 1 gives us 3.2 AMUs. So this is our average atomic mass. For barium is 3.2 AMUs. Now let's continue on with our average atomic mass, or AAM, with magnesium. So we just got an example of how to calculate the average atomic mass for bears, and pretty easy numbers out of 10. And we're going to do the same kind of formula. So again, this is going to be equal to essentially mass 1 times decimal 1 plus mass 2 times decimal 2 plus however many isotopes there are. So this can go on, hopefully not indefinitely, but for a long time for sure. And so we can add these for, you don't need to really for one isotope, because it's just the mass 1 times the decimal would be 100%. So it would be 1. So if there's only one kind of isotope of some things, and there are, then it would just give you the mass number. But if we have 2 masses, then we have to figure out how much each one contributes. And again, all these contributions should add up to 100% or to 1 in decimal form, and that'll affect the number. So let's move on with magnesium. So I have 3 isotopes of magnesium. Magnesium is, if you'll remember, there's magnesium 24, there is magnesium 25, and there is magnesium 26. So the thing that makes magnesium is its number of protons, and its number of protons is 12. So here we know that this thing has 12 protons, but also 12 neutrons. This thing has 12 protons, but 13 neutrons, and this thing has 12 protons, and 14 neutrons. So that's where the mass number comes from. And what we can say about these things is that they each have a contribution. So if we look back on our old sheet, or back on the previous video, we had the percent abundances. So let's just write this down, what its mass is, and then what its percent abundance is. And so here what we have is the mass of this thing is roughly 24 AMUs. Here it's roughly 25 AMUs, and here it's roughly 26 AMUs. And then our percentages are about 78.99 5%. This one is 10%. And then this one is 11.01%. And again, the way we got those percentages was went through a mass spec and it spit out these numbers, right? It essentially like counted them and sorted them based on their mass. So we have that. What we're really going to need is the decimal form. And there's a way to do it with percent abundance, but I prefer to do it in decimal form, so we're just going to divide these numbers by 100. And now what we can do is we can plug this into our equation, which is the same as before. Average atomic mass is equal to this thing. And here, because we have 3 isotopes, we're going to have 3 contributions. So this thing right here is considered like a contribution. And we'll add up all the contributions. So this thing right here inside the parentheses is the contribution. So we're going to figure out the contribution for each. And the way that we're going to do that is for these things, we're going to add up the mass. So 24 times its decimal form, percent abundance, which is 0.7899. And then we'll do that again for the isotope of 25. And the isotope of 25 is less abundant. It's only 10% of the time, or 0.100 in decimal form. And then we have isotope 26, which is roughly 11%, or 0.1101 in decimal form. And so when we do these things, what we'll get are these numbers. So this number right here will be 18.9576 for this number. For this number, we'll add to that 2.5, right, just based on that. And then this number right here will be 2.8626. So these are our contributions. So because this is such a big percentage, this contributes a lot. Because this is a smaller percentage, this contributes less. This is a smaller percentage, it contributes less. And so when we add this all together, the average atomic mass is going to be equal to these 3 numbers added together. And this gives us 24.3202 AMUs. Now this number, you'll notice if you look on the periodic table, it's pretty close to the number on the periodic table. It's the number below the symbol on the periodic table, and it's pretty close. So if we look at the periodic table, we get 24.305. Sometimes it's going to be 24.31. So this is pretty close, but it's not exactly correct. And the reason why it's not exactly correct is because our masses are actually just slightly off. And so what we'll find out later on is that that the masses are based on the number of protons and neutrons. But if you'll remember, protons and neutrons are slightly different in mass. And so because they're slightly different in mass, sometimes you'll get a number right above, right below 1. And so if we use the actual masses based on those things, we get that magnesium 24 is actually weighs 23.985042 AMU. Magnesium 25 weighs 24.985837 AMUs, and that magnesium 26 weighs 25.982593 AMUs. And so what we're going to do is we're going to do this calculation again. And I'm going to move through this one a little bit more quickly because we've already seen it. The contribution is just the mass times the decimal form. And then we're going to do the same thing with the other 2 isotopes. And we're just going to use the more accurate masses. So the other masses weren't wrong per se, but they weren't the best representations that we could use. And then for the next one, I'm just going to jump down here. And again, this is each one of these things is considered a contribution. And when we do this again, what we're going to get is a number much closer to the correct value. So we would get 20 4.305. And what we'll get is that this number is actually the right number on the periodic table. So it's actually like 0, 5, and then it goes on and on and on. But this number actually matches the number on the periodic table, and it is in AMUs. So the reason why these numbers might be slightly different than the ones on the periodic table is because, again, this just counts the number of protons and neutrons, but doesn't take into effect essentially that neutrons weigh a little bit more than protons. All right, hopefully this video has been helpful. Have a great day, guys.